Hi class, this week's lab is involving empirical formulas. So the objectives of this lab is what is an empirical formula, observe the laws of conservation of mass and definite proportions, determine the empirical formula of a compound from experimental data. So empirical versus molecular. The empirical formula states the ratios of the elements that make up the molecule, while molecular formulas specify the amounts of each element exactly. The easiest way for me to explain this is first pay attention to the word molecular. We're dealing with nonmetals in here, and you can see based on here, this is the molecular formula of, I believe this is glucose. But if you reduce everything down as much as you can, you get the empirical formula. The way that I explain this that hopefully makes sense is this is the skeleton, this is the person on the outside layer. So a lot of molecules, compounds, will all have the same backbone, the same skeleton. But what makes them different is the outer layer. So this is the skeleton, this is everything else. Excuse me. So a molecular formula may be simplified to an empirical formula. This is why you never reduce molecular formulas down in their existing form unless you're trying to get the empirical formula. Because like I said, a lot of compounds will all have the same empirical formula, but then when they're branched out, they'll have different molecular formulas. To be simplified, all components must be able to be reduced to a small whole numbers. So as you can see, the 2's left because this can all be reduced by 6, leaving the 2 behind. You can no longer reduce when you can no longer get whole numbers. So if we were try to reduce this by 2 on everything, we're going to get half numbers, and that's a no-no. Molecular versus empirical. So some compounds will already be in their empirical form. Carbon dioxide, you cannot reduce down. Water cannot be reduced down. But as you start getting into other compounds, you can see they can be reduced down. And if you can reduce it down in the form of being asked for empirical formula, you should. If you're trying to keep it as a molecular formula, you do not reduce these down. Empirical formula, the lowest whole number ratios of atoms. So here's just an example. We have acetic acid. So we can reduce this down by 2, but not by 4. So when we reduce each subscript, we end up with CH2, which is also, if I believe right, same for glucose. So this is another example of why you don't reduce down unless it's exactly asking for an empirical formula of it. Another one down here is benzene. We can reduce both of these by 6, which ends up giving us the backbone of CH, and many, many other compounds have this as their empirical formula. Here are steps to determining the empirical formula. This is just general, and we will also be following these rules in this lab. So problems usually given in mass of atoms or percentage of atoms in a compound. Majority are, at least when I've seen, are given in percentage. We are doing our labs in mass, so we are skipping this percentage part, but it's not difficult. If you're ever given a problem with percentage, you never have to worry about this equaling 100. The person who's providing the problem should make sure that there's no errors regarding that, and then you simply make it out of 100. So this 40.68% carbon would now be 40.68 grams. 5.08% would be 5.08 grams, and so forth. By doing this, you are now actually at this step, and then you can go forward. Here's an example of a problem. I didn't put the wording of the problem, but if you're provided a problem that would be giving you percentage, you simply follow the steps that are here. This is a lot more condensed, but it displays every step and exactly how they got the empirical formula of vanillin. So this is more for you guys in case you needed a sample problem. So now we come to the lab. So in this lab, we are determining the empirical formula of magnesium chloride. We will have the mass of the solid before the reaction, and then we'll have the mass of the product after the reaction. We determine the mass of chloride by taking the mass of the product and the mass of magnesium. So by taking these, we're figuring out the mass of magnesium, which only will provide us with the mass of the chloride once we subtract this from the product. This has to do with the law of conservation of mass. It simply means that whatever the mass of the reactants are, they have to equal the mass of the products as long as the specified conditions, meaning this should be enclosed so you can account for every single thing. We're not worrying about the hydrogen in this. It is accounted for, but we have removed it from this problem. So we're only focusing on magnesium and chloride. But overall, yes, it still follows the law of conservation of mass, that everything on this side, all components, when added together, will equal whatever's added on this side. But the way the lab is set up, we don't even have to touch hydrogen in this, and we still follow the law of conservation of mass. So overall, the lab, prepare a compound of magnesium metal to react with chloride. This experiment and calculations will determine the empirical formula and the correct compound. Since it's an ionics we do not reduce down. It will be in its simplest form as long as your calculations are correct. So here's the lab. Again, I always specify that you need to read the lab, the PDF completely. I give you an overview, but I don't give you details in specific details, just the overview. That is meant on purpose so that you will read the instructions. Okay, so we set up the lab equipment, which is pretty much here. This is your stand, you have an evaporating dish, and you have a watch glass on top with wire gauze, which will allow you to heat. It's going to be above the Bunsen burner. Weigh everything. This is an analytical balance. When you weigh it, you will close all the doors because these are so sensitive that even air conditioning systems sometimes affect the mass on them. And you always want to weigh everything at the same room temperature because even temperature can affect your the results on a balance. So in this lab, you're going to have your metal, and this is what a metal looks like in this picture here. You can see it's a metal ribbon. And you have an evaporating dish, and you are continually adding HCl until the reaction stops. And how does that reaction stop? So you can see what once the acid has been added, it starts to really bubble, and it's really vigorous. So this is you want to be able to control this reaction. But when does it stop? Well, it stops when you can see no metal left and no more new bubbles being produced. You'll probably have bubbles on the side of the walls, but they're not new bubbles. They were existing. So when you see no more new bubbles produced and the metal is completely gone, the reaction is done. From there, what you'll do is you'll heat the solution very slow with a gentle flame, and that will allow the excess HCl and the water to evaporate away. Then it's cooled, and you weigh it as instructed in the procedures. By the way, with magnesium, when you're doing a reaction like this, it would not be a problem. But in Chem 10, there was a lab that you had the magnesium metal and you had to light it in the flame, and it said don't look at it. The reason why you don't look at it is it's intensely bright and it could hurt your eyes and even burn in there. It's just really, really, really intensely white. So you never look at magnesium metal though in reactions when you're dealing with flames. Okay, so I've set this up. Again, never follow my numbers. I've changed my numbers so they should not match anything on LabFlow. But I followed the rules, and the numbers I provide for you are usually the numbers that match the sig figs. Okay, so we have a mass of a watch glass and evaporating dish, and that is this clear teacup saucer and this porcelain dish at the bottom. I think it's porcelain. Mass of watch glass and evaporating dish of magnesium ribbon. So this would be before the experiment starts, and then this is after the experiment is done. So after it's been reacted. So the first thing you do is you determine the magnesium mass. I provided letters. They don't on your lab, but this makes it easier for you to follow steps. So calculate the magnesium mass, and that is simply subtracting the watch glass and evaporating dish from everything that you have, so then you'll only have the magnesium ribbon amount. The second one is calculate the product. So it's now you have C, which is after the experiment, and you are subtracting the watch glass and evaporating dish. So that gives you a mass. Now, because of law of conservation, the amount that you have on one side should equal the other. So we know what our magnesium is, we know what our product is. We now, through subtraction of these two, we can determine the result, the leftover. Subtracting 1.04 by 0.20 gives us our mass of our chloride. But we're not done. We've just got the foundation and we still need to go forward with this. So I've just copied these questions. They are straight from the first one, so number 3. But number 4, now that we know our mass of magnesium, we can't work in masses. Masses don't work in chemistry for us. We need to convert this to moles. So this is just the molar mass, and I have my molar mass of magnesium, still following the sig fig rules. Calculate the moles of chlorine. So we also have our chlorine. We have it right here, number 3. I have divided it by the molar mass, and it also gives me my moles of chlorine. Now, we need to determine the empirical formula. We have moles for both. We set them up. We always divide by the one with the smallest number. The smallest number is magnesium, so we divide that. That gives 1. We divide the chlorine by the smallest number, which was magnesium, and it gives us a 2.9. We can round this up to 3, which gives my empirical formula as MgCl3. If you get different results, try to remember never to follow exactly what mine is. It's purposely not supposed to match yours, but it's to give you the steps, and always just follow your steps. It will never do you wrong. Make sure you always follow sig fig rules as well. And if you were to get something here that was like 1.5 and 1, then you multiply those by 2, by 3, until you get whole numbers for both. That will be your empirical formula. There is a problem on the quiz that I don't agree with, so I'm giving you the answer if you happen to get this problem. Now keep in mind, this is not the entire problem. This is one. So on this problem, you're given a list of compounds, and you have to determine if they are empirical formula or not empirical formula. I got everything right, but this one. They marked this one wrong, and I disagree with it. So I'm giving you the answer. Because ions, ionic bonded compounds, cannot be empirical formulas, as far as I've always understood. So they marked this when I put that it wasn't its empirical formula incorrect. So I changed it to not an empirical formula, and they marked it correct. The problem is potassium's a metal, and oxalate is a polyatomic ion. If you reduce this down, it's not going to be correct, and it's no longer an oxalate ion. So I disagree with this. So if you may not get this problem, and I'm only giving you one answer of many on here you have to answer. So don't come back and say, well, you gave me the answer. No, I gave you the answer to the one that marked me wrong. There's like 5 other compounds on here you have to answer for, and those follow the general rules. Tips: watch the videos and pay attention. Some questions on the quiz, the answers can be found in the videos, which I did not cover in this lecture because the videos do a very good job of it. My outcome, I changed my numbers. Follow your calculations, follow your sig fig rules, your rounding rules. If you need help, make sure that you try to get my help before Friday afternoon, late afternoon. Post on pronto. You guys are doing a great job with that. I'm really happy that you guys are reaching out to each other, and keep doing that.